Hi there, my name is Colin. Today I'm going to be talking about a technique I'll be proposing as a potential method for decelerating spacecraft moving through magnetic fields that are also moving at relativistic speeds. Obviously, a lot of big words here. Some context for why I'm making this video. This video is being added as kind of a supplement material for the poster I'm presenting at the Interstellar Research Group's 2021 symposium. Usually, for a lot of these conferences, you have a poster, you go do your talk, everyone's really happy. In our case, it seemed like they only had enough time for me to do a poster. So in addition to the poster and then some links I'll be attaching down below to the white paper, which as recording this video will be in preprint form, but is actually planned to be released in an academic journal. Not sure I'm not allowed to reveal the name of it yet, so I won't yet. But when that gets updated, I'll post that below. So in addition to the paper and the poster at this session, for those of you who like kind of an audiovisual explanation from the author, or you missed me, talking about my poster, this video should be hopefully I'm expecting a 15 to 20 minute overview of the topic. We'll see how quickly I can actually, or how thoroughly I can get through this in a given amount of time. But that gives you some context. So without further ado, we'll get into this topic. And we'll jump right into it. So first off, overview for kind of the, what's the overall abstract for this talk. And the abstract, we'll just quickly kind of read off, is that if you're having a spacecraft moving at relativistic speeds and you're trying to break it with, proposed ideas, those proposed ideas are either speed limited, distance limited. So both of those, you can only go to a certain speed of light for them to work. Distance limited, you can't really break them, completely stop them as they go through this given, other interstellar solar system, or the given technology that's being proposed to stop the spacecraft is not only infeasible due to the engineering challenges required, but as I'll elucidate in those given areas, that there's actually white papers talking about that, even within a few thousand years, given current understanding of fundamental physics, these techniques will probably be very unlikely to work. Again, physics may change, it almost certainly will change, but we can only go off of what we know currently as of recording this video. So given all that, I'm proposing in this talk that there is an actually very unexplored method that's used a lot in a lot of our applications in terms of roller coasters use this a lot. Trains will use this a lot. That there are actually methods of using this concept called eddy current braking. That if you apply this technique to spacecraft moving at interstellar relativistic speeds, that hypothetically it should be able to solve the problem, given that it solves the problem at lower speeds. Obviously, very hypothetical, but given, as I'll show in the next few slides, that the other techniques aren't really great, and actually they're pretty bad if we want to expect to stop. This is something that we should explore as researchers as a way of potentially slowing down a spacecraft. So, quick overview. I'll talk about, here are the previous braking methods. I'll introduce eddy currents for those who are familiar, give you an intuition, what things you have to worry about in regards to the design of your spacecraft if you're going to use this method. You're going to look at, there's actually some things regarding power generation that you can actually get out of it. Hypothetically, again, I'll show you the calculations there, deceleration distance, and then of course, if I've convinced you, okay, this is a technique, hypothetically, it works in sub-relativistic speeds on Earth for other applications. It should work in space, and we should pursue it, given that we don't really have a great method of actually slowing down spacecraft, given the other previous ideas. What's the future work look like for that? So first up, previous braking methods. We'll go over them kind of briefly. I'm not going to go super detailed, but at least let you know what the lay of the land looks like. The first one, for those of you who are big reaction engine fans, is antimatter. Antimatter, for those who are familiar, we're all made of matter. If you go talk to a particle physicist and you go look at the decay of, I think it's beta particles off the top of my head, there will actually be equivalent antimatter particles that are generated that if you had basically an antimatter version of me, and you smashed them into me, I would annihilate into pure energy using a certain German physicist's famous E=mc² formula, and then you get a lot of energy out of that, and it's a pretty explosive reaction. So that's this is kind of this is the first idea. If you want to use antimatter engines, is a potential application. The problem is is that, okay, well, how much does a gram of antimatter cost? It is currently, as you can see here, $2,700 trillion per gram. And to give it, even better perspective, if you were to say, okay, maybe that's expensive. Let's say I want to use uranium as a trade-off. How would that compare? Uranium obviously isn't going to be as potent as we know from nuclear bombs, which seems kind of absurd given how explosive those things are. But uranium, if you look at the energy that you get out of combining those fissioning particles from that, it's about 1,000 times less potent if you were to make a uranium engine to slow down the spacecraft. But if you look at the cost per gram of uranium, it's about 1 trillion times cheaper than antimatter. So one thing you have to look at, of course, is you want to make the spacecraft cheap, because the main reason why we're not interstellar right now is because it's too expensive. You're looking at very vast challenges in terms of making antimatter engines cheaper. In addition, okay, cool, you can make kilograms, let's say, of antimatter. Your next problem is to store the thing for longer than, in this case, 17 minutes. That is currently our best attempt at trying to store antimatter. There are approaches that could potentially extend it to maybe hours, but when you're looking at an interstellar mission where you're looking to go optimistically 20 years, you need to store it obviously a few orders of magnitude. And this is a topic I've looked at. Given that I'm on a computer, this isn't a formal lecture, I can do this. There's a great white paper that I've linked over here called the Plasma and Trap-Based Techniques for Science with Antimatter. That is a really great lay of the land for, hey, if we wanted to look at pushing this technology, how would we go about doing that? You can go ahead and read it for yourself, but the author, at least myself reading through it, is that looking at these different techniques, there's not really an obvious clear path forward, even given our current understanding of physics. Even the best techniques that they propose here can maybe bump them up to a few hours. In addition to that, there's not really an economic incentive to develop this technology. So there's a lot of factors going against antimatter. We'll put it that way. So it is potentially a solution, but as we'll show here, I'm proposing that the solution in this paper will be a lot easier to do than reducing the cost and storage time of antimatter by factors of 1 trillion, or hundreds of trillion. We'll put it that way. So that's antimatter, one proposed method. Another method, magnetic sails. Basically, you have a conductive loop of a certain diameter that's unfurled. You can it's going through. Space is actually not completely a vacuum. There's actually charged particles of hydrogen, various other dust that you can actually, if you're going through it, you can actually use that to slow it down. Of course, if you're in going through another solar system, there's a magnetic wind of solar wind, or there's a solar wind that you can actually use in magnetic sails to slow it down. There's been papers there's a paper that looked at this. I've linked to the new Atlas article that links to the actual white paper that you can go see down here if you click on that. Basically, what they looked at is, yes, this could work if you want to use solar wind of the other interstellar solar system. The problem is that you could only the spacecraft could only be going at about 0.3% the speed of light if you want to use this method. So yes, this could work, but you're gonna have to you can't go anywhere close to significant relativistic speeds. So not really an interesting or very attractive idea. So okay, magnetic sails. Let's try solar sails. Maybe that's better. You can use radiation in addition to some solar wind. There was additionally, I'll pull up the other white paper you can take a look at. This paper by Heller et al. The deceleration, using photon sails at Alpha Centauri. What they take a look at. Some downsides for this is that, of course, okay, if you're using the solar wind on the solar sail, you can't generate power or significant amounts of power. You might be able to do some interesting, we'll make the solar sail out of solar panels or something crazy like that. Or, something that can get, if you have ionizing radiation coming in, you can harvest some energy, not significant amounts, but you probably could do it. But if you look at the sail size required, if you're moving at 20% the speed of light, you need 316 to the power of 2 square meters of a sail. And for those of you who are like, okay, I'm I'm the one weird world that doesn't use metric. I don't really have a good intuition how big that is. Let's say you basically have to make this sail about 3 football fields in size, uh, to do this, and that's moving at 20% the speed of light. So, feasible technically, big engineering challenge because you have to have, big, a big space to make, that size of sail, get up to space. Maybe you could do some in-space manufacturing. That's potentially a possibility. But again, if you're going to scale up to more significant speeds at the speed of light, you're looking at, orders. You're going to scale with, a squared. Your scaling is basically squared as well there. So obviously it's not going to scale well if you want to go faster. So, okay, you can use solar sails, but you choose your poison basically at this point. Finally, one more speculative method that's still research preliminary, but I wanted to be as thorough as possible. Okay, what are different techniques that you can use? Magnetic shield breaking. Basically, you take the planet. If you're going through the atmosphere of, let's say, a star or a planetary body, there'll actually be some neutrals or basically an ionosphere that you can use a rotating magnetic field, as I showed in this research by Kirtley et al. To slow down. In this case, this research was worked on, using planetary bodies. Research is still preliminary. It could be potentially, useful. You do have to, generate the power to create this rotating magnetic field. So, something to bear in mind here. Again, something that's still speculative. There's a NIAC grant or a NASA Innovative Advanced Concept grant that's going into researching this method. Another potential one. So I figured I'd, include it here to be fairly thorough about this idea. So those are the 4 methods. We have antimatter. Downside is it, technologically, you're looking at trillions of orders of magnitude in terms of storage time and price point reduction. Magnetic sail is, of course, speed limited. You can only go at a fraction of a percent the speed of light if you want to use this. Solar sails, if you want to make really, really big size sails, I guess go for it and keep making them bigger if you want to go significant speeds of light. And then, of course, you might have to, if you make, look at the unfurling problem and stuff like that. Potentially, magnetic shell could be potentially possible. Right now, they only looked at planets, which if you look at, if you want to decelerate a spacecraft moving at a significant fraction of the speed of light over the distance of a planetary atmosphere, in addition to a lot of thermal issues that you would have, the deceleration, forces that you'll see, and as I'll calculate later in my papers, you're looking at pretty big decelerations here. So that's something you have to consider if you want to use magnetic shell. So the conclusion of this overview is that there's not great solutions to slowing them down. There are kind of solutions, but if you're moving at relativistic speeds, so is there potentially a better one? And that's, 10 minutes later, this is what we'll talk about, the eddy current breaking, which is a potential solution that I'm proposing in this paper. So we'll kind of briefly go over that. So first off, the intuition for those who aren't familiar. The visualization I'd like to show everyone today is that a magnet, when traversing across a nearby conductive object, experiences a drag force. This little video will show a demonstration on this on the bottom. Right here, you have a skateboard moving over the top of a copper plate. Under the skateboard, there's a big fat magnet that they have, and as you can notice from this video, when that magnet travels over this conductive copper plate, this skateboard slows down as it experiences this idea, which I'll show in the next slide, called an eddy current force. This eddy current force, as it's shown here, when a conductive material moves through this magnetic field, it'll experience these little, basically electronic eddy currents, or rotating, circulating, charged, current paths, and it'll create basically, there's like another induced electric field, creates a magnetic field, which creates a force in the opposite direction, which enables this, this kind of braking force that you see here in this video to occur. So what I'm thinking, as this technique is used a lot by roller coasters to slow down, trains sometimes to slow down, is that could this potentially be used to move a spacecraft made out of conducting material through a magnetic field, stellar magnetic field. You can use a planetary one, but you'll see because of the deceleration forces, you'll likely want to use a stellar magnetic field. Could you slow a spacecraft moving at relativistic speeds using this technique? And if you did, it would probably look like a certain spacecraft that many of us are familiar with listed above, As you can see, that there are very similar analogies between coming out of hyperspace and slowing down your skateboard. Yeah, so that was kind of actually the visual intuition where, look at that, the skateboard kind of looks like, as it slows down, very similar kind of visual effect here. So maybe there's a way we can harness that. So, all right, we're going to talk about this. Okay, we have a magnetic strip. It has a certain magnetic field going through it. And as it's traveling at a given speed, there's a force that acts in the opposite direction. So this is a quick little visual to kind of visually demonstrate this idea. So what are the different theories or formulas that you have to pay attention to harness this? This is the, again, this is all hypothetical. I'm pulling these mostly from, one major paper that was posted in the American Journal of Physics on magnetic braking, that they did a simple theory and experiment where, they took conductive material, magnet, ran it over a bunch of times and then see if they could develop the formula to demonstrate the force induced on this given magnet. They were able to, pardon my German there for a second, they were able to come up with a formula with a certain amount, these given variables. I'll briefly touch on all of them, talk more about them as we go through a theoretical design, using this formula of how you could take the spacecraft or design a spacecraft to use this eddy current. But primary factors is you need the thickness of the metal strip. You need the electroconductivity of the strip. As you see here, if it's more conductive, the eddy current forces are going to be stronger. Net magnetic field, or the magnetic field from the star going through the plate. How quickly the metal strip is going through, interstellar space. Induced current density, which is, that this will be basically, it's the vector that's, multiplied from, the cross product that gives you the force out of this. Change in time. That's this, integral. In this case, we're mostly focused on, this simplification for, one dimension. And a braking force, of course. The L and W are the dimensions of the sail, the cross section at least. Theta, as this formula was originally pulled from this Weidrich et al. Magnetic braking paper. In their experimental setup, they had the magnetic, or the magnetic perpendicular to the conductive material. In this case, in our case, there's actually a use case for having your conductive, sail as it's going through the magnetic field not being perpendicular to that force. So there's going to be at least I'm proposing that there'll be likely, a sign product you have to put in there where theta is, okay, the angle between your perpendicular magnetic field and your conductive sail. And then A here is this alpha here is a dimensionless quality calculated by the formulas. This part, to be honest, they explain this paper. They give I would refer to the paper if you want a better detail about why they use this alpha. It was kind of a correction factor that they use to make the basically their linear fit or to make their formulas match up with the experimental data. But it has something to do with treating the plate as kind of like a resistor. They basically made like a basic electrical circuit and of the interaction between these two forces, and then derive these formulas from it. I would highly refer to this paper as even reading through it and talking to some people about it. Not fully sure I understand why this alpha correction factor is there, but it makes the data work out, so we can at least go with that. So, all right, I've proposed, okay, this is eddy current forces. It creates this braking effect. This is the formula that you would likely need to work with if you want to design the spacecraft. Let's go ahead and design a spacecraft. Again, there's a lot big with design parameter space. You can make the sail bigger, smaller, certain speeds. In this case, I wanted to show, just give you a quick design example to give people ideas about, okay, what sort of factors are you really looking at if you're designing your spacecraft to decelerate using this method. So for this example, we're going to use a 1 gram, 1.7 nanometer thick sail made of graphene that's about 16 by 16 meters wide. It'll be traveling at 8% the speed of light, and it'll be slowed down by means of this eddy current braking method. So the criteria, which I'll elaborate on in the next few slides, is that you need to figure out what the fastest time you can stop your spacecraft is without vaporizing it, And then you need to make sure that the time you actually decelerate using this eddy current force is less than that given time. As I'll explain in a second, as you break, and then you show here, as the conductive sail is going through a magnetic field or any conductive strip, the reason it's slowing down, or where that all that energy basically that's getting created, is going into the eddy currents within the conductive strip, as you see. We'll explain in a second, and that energy will actually start to heat up the conductive material. So these two videos that I'm showing here kind of elucidate that. Off to the left here, we have a guy holding a big magnet in his hand. We have over here a spinning conductive disc. Then as he puts the magnet over the spinning conductive disc, much like the slide that we show a few slides back, there will be induced eddy current forces that will slow down the disc. If you want an audio demonstration, I highly suggest this video up here. Both of these videos are pulled in that, where you can actually hear the disc slowing down. And then as the disc slows down, off to the right here, you'll actually see the disc begin to heat up. That comes from these induced eddy current forces, which will then heat up this conductive material. So hopefully, kind of got all that. If you have a spacecraft moving through the vacuum of space, you need to get rid of that heat, or else you vaporize your spacecraft, which is not good. As you don't really, for anybody who's familiar with heat transfer mechanisms, conduction, convection, radiation, your spacecraft isn't touching anything else other than the vacuum of space. No conduction, convection, not really significant because you're in basically a vacuum. So you need to heat away, radiate this heat away. So if you do, basically the first order vaporization calculation, assuming that all the energy of the spacecraft is converted into, all the kinetic energy of the spacecraft, is converted into, a heat load, and you need to radiate that heat away. You can take, the kinetic energy over Stefan Boltzmann, your favorite radiation calculation here, where you have the emissivity of the spacecraft. Always have a fun time saying that word. The surface area of the spacecraft, in this case, because it's so thin, we'll say it's approximately a 2D cross-section, the 16 by 16 meters, the Stefan Boltzmann constant, and then the change in temperature. In our case, the change in temperature is the melting point of graphene to basically 3 degrees Kelvin, which is the temperature of outer space, roughly. If you do those calculations, you want to see, okay, what's the fastest stopping time moving at this given speed that can be achieved without vaporizing the spacecraft? You get 121 seconds. This calculation, again, refer to my white paper down below if you want, the actual details of this calculation. This calculation assumes a conservative emissivity of 0.2 for graphene, because that's what we can currently achieve. This number will obviously gets reduced by a fifth if you can get a emissivity of about 1. So there's obviously a lot of room to improve, and you can actually get smaller cross-sectional areas if you're able to improve the emissivity of the given material, or of course the melting point. And then, of course, because it's all getting heated, you're technically generating power. You just do a quick, power generation calculation here, and you find, okay, you get about 26 watts of heat that's placed into the spacecraft for this given deceleration time. So that's pretty cool if you want to heat up anything else on the spacecraft or use that for power. So that's the vaporization calculation. Now, we have to make sure, okay, we have this given time. We need to make sure the spacecraft decelerates, that it takes longer for the spacecraft to decelerate than this vaporization calculation, because if it goes faster than this vaporization calculation, you're going to vaporize the spacecraft. So in order to figure out, okay, how quickly or, how slowly do we need to decelerate the spacecraft so we don't need to worry about, these sort of problems? You can use the magnetic drag force formula that we showed a few slides ago. Again, refer to the paper if you want the full in detail calculations. But from this example, you get about 189 newtons of deceleration, assuming these parameters for the other parts. One thing to note is that the magnetic field going into the spacecraft is not a driving factor. So if you notice, what theta angle that we're using for this calculation, it's actually a very small amount of the total maximum magnetic field strength that can be provided by the stellar magnetic field or whatever you're going through. Something to keep in mind. From that calculation, okay, you can do a conservation of momentum calculation here. In our case, because we're moving at 8% the speed of light, if you do a relativistic mass calculation, or okay, how much heavier does your spacecraft get for that given speed? It only gets about 4% greater. This analysis, that wasn't deemed that wasn't deemed super significant, so we didn't factor in the relativistic effects. Obviously, you can go through that. You add whatever, multiply whatever, whatever time you need to correction factor if you want to do that. In this case, it didn't significantly contribute to the deceleration time, so we ignored it. And then you can figure out that, okay, if you do the conservation, your total momentum required to decelerate the spacecraft over the force that we derived from moving through the magnetic field, you get that the deceleration time through the magnetic field using that force is about 127 seconds, which, if we look at our vaporization calculation, is greater than 121 seconds. So given it'll take longer than 121 seconds using this conservation momentum and force calculation, that we can say, okay, hypothetically, on paper, this technique should be able to decelerate the spacecraft without vaporizing it. Again, still hypothetical, still need to go through the work. Some other interesting conclusions, if you pull, given those calculations, you can actually decelerate your spacecraft, again, in 127 seconds, which is pretty significant, actually. If you look at the, just do your favorite kinematic equations for how, what sort of forces you're looking at from that deceleration speed, that's about 19,000 Gs. If you look at the deceleration rate or the acceleration rating of the best accelerometers that the military uses, currently our best sensors can decelerate at about 15,000 Gs. So in terms of, okay, hey, if you're looking at, is this within, technological feasible range of development? Yes, this should be, I haven't looked at, okay, creating the MEMS devices to survive those forces, but, this should be within, a technological step for us. We just need the motivation. And okay, here you go. Here's the motivation right here. You can technically, there should be a way to extrapolate current accelerometer technology to be able to survive that. And then, of course, if you look at the deceleration distance, it's about 1.53 gigameters, or 10 to the 9 meters, which is going to be less than 1.7. In this case, the diameter of Alpha Centauri. I use the diameter of Alpha Centauri here as I assume that, okay, the magnetic field of Alpha Centauri should be at least as wide as the star itself. From my reading online, I couldn't find any great data to see how far out the magnetic field of that, the star goes and or how strong it is. The first few missions will probably go and figure that out the fun way. But this at least gives you a general idea of, okay, if it can stop within the diameter of a given star, that's probably pretty good. And again, another note, talking about like the other previous techniques, like the magnetosphere breaking, as that technique is primarily driven by, planetary atmospheres. If you look at, what's the size of a star given versus the size of a planet, you're looking at, okay, if you want to use that technique to decelerate your spacecraft through a planet, you're looking at orders of magnitude greater G forces. And of course, they're dissipating all that energy, at least from what I see, there's not really an obvious method of dissipating all that heat. So, that's a downside of, that potential technique, but, still should explore it, but something else to bear in mind if you're looking at, okay, what distance are you decelerating over? So in conclusion, about 30 minutes worth of talking. Eddy current forces are a potential method to slow down spacecraft moving at relativistic speeds. Again, it works by you have a spacecraft made of conductive material. It travels at a given speed through a magnetic field. And because of the eddy current forces induced in it, it induces a force moving in the opposite direction, which will slow it down. This force, of course, will generate heat, which in addition to generate power, needs to be dissipated away. So the two things that if you're going to explore, okay, in addition to let's send some metal spacecraft through magnetic fields and see if this, if we see a similar effect here. A couple things that you need to look at if you want to use and improve this technology is that if we go back to our formulas for the vaporization calculations, if you can increase the melting point of your sail, that's the biggest gain as from your radiation calculation, your temperature differential, or how much energy you can absorb into it, scales to the fourth. So if you increase the melting point of your material, that's obviously going to help you slow down faster or make the sail size smaller. And then, of course, the acceleration ratings of spacecraft and electronics, we'll need to improve those. Because if you can do that, you can slow down even quicker. You can actually have, if the magnetic field only goes out so far, you can actually slow down at a greater speed and take advantage of that fact that you have a smaller runway, basically to slow down your sail. Another thing, and this was something where I think we'll have to likely, try to do this in, do an experimental setup. But a lot of this, a lot of the techniques here, of course, this was a first order calculation just to show, hey, we can use this technique potentially to break a spacecraft. Eddy current techniques, if you look at a lot of them, they require alternating magnetic fields. And at least for me, I'm not, my background, and I didn't dive that deep into the literature because that would have been, it would end up turning to like a master's thesis basically. And, I wanted to at least get this idea out so we can start thinking about this. But I'm still not quite, I'm still not quite sure, given the non-uniform nature of stellar magnetic fields, how much that factor is going to contribute, and or whether we'll need, control systems. Because if we assume, okay, the magnetic field is perfectly uniform, well, in order eddy current forces to work, you need the magnetic field to alternate a bit. So you may need, the spacecraft to actually tilt a little bit as it's going through the field, so you actually get those forces acting on the spacecraft. Or maybe the magnetic fields are just inherently non-uniform, so you don't have to worry about that. Something else to consider and keep top of mind. Didn't look into those details, but at least want to kind of highlight that as something for future work. I want to say thank you very much. Here are some references, and I want to especially highlight as a question that comes up is like, okay, we have this method of eddy current breaking obviously works for roller coasters and trains, but and on paper it should work for spacecraft. I want to highlight a paper that was recently put out by some analysis on the Juno mission, where there's actually some researchers listed here that actually noticed that there's eddy currents generated on the spacecraft as the spacecraft moved through Jupiter's magnetosphere. They were actually analyzing it just to see, okay, what are the forces? There's some interesting, visuals that they show here. But talking to the researchers, I asked them, hey, would you see any sort of force being put on the spacecraft? And they, respond back, yes, actually, you would. It probably fairly minor, given, how slowly the spacecraft is moving relative, looking at the formulas looked here below. We haven't looked at it, but yes, that technically would be a force that you would see on the spacecraft from this eddy current being generated from the Juno spacecraft moving through Jupiter's magnetosphere. Wanted to highlight their work and give them a shout out. And then, if you're looking at other papers for, magnetosphere generating, or, some of the other previous research, here's all that listed here if you want to go look at it. I'll post, of course, the slides below. You can look at the white paper that we either preprint or in an academic article if you want to see the actual physical calculations and me going through it step by step down below. But I want to say thank you very much. I'm sorry for going, 34, 35 minutes. But this is, should be a thorough overview of, okay, breaking methods. Here's the previous work. Here's this, pros and cons of both. Here's a potential solution. Here's, if you want to use this potential solution, here are at least the first order design things that you need to pay attention to. And then, okay, future work, resources to look further. Feel free to post questions down below or shoot me an email. I'll be sure to at least include my academic email down below if you have questions. I want to say thank you very much. Thank you to the Interstellar Research Group for allowing me to present this work. And I guess YouTube for hosting this and posting comments down below. But yeah, thank you very much. Hope you enjoyed the talk and catch you guys around.